thanks so much. And everybody, welcome. Thanks for coming. I'm really excited to that we have this much interest in a topic I'm a bit passionate about, spray dryers. I've been doing it my career. You can only cram so much into a 30-minute webinar. So we've picked a few topics here. We hope to leave you with a few nuggets of useful information, maybe help you raise a few questions of things you can look at yourselves in your plants or in your operation. And of course, things that you can come back to us with afterwards. Please feel free to reach out to me by this email shown on the screen right now. And we can continue a dialogue after this. About a portion, a third to a half, is going to be some theoretical information, and then we'll dive into some practical sides of troubleshooting. So with that, I'm going to begin. If I can advance the slide. All right. Pardon me for not mastering the technology here. All right. Very briefly, if you're not familiar with Caloris, a quick introduction. We are a supplier of new equipment and upgrades for evaporators, spray dryers, and membrane filtration, mainly for the food, dairy, and beverage industries. That's the extent of the commercial for today. But if you do have questions in that realm, feel free to reach out to us. I like to leave people with some useful information you can take away from this, use on a different day. If you're hungry for a basic textbook that includes information about spray drying, this book, I hate to advertise for my competitors, but the book is really quite good. It's from GEA. It's called Milk Powder Technology. You can Google it that way. Don't be put off if you don't work in dairy that it's a milk powder technology book. It really forms a good foundation for evaporation and spray drying. When I hire a new employee or have somebody new working with me, I do a training for a new plant. I make this exact same suggestion to go get this book. It's downloadable for free. Again, just Google milk powder technology and you'll come up with it. If you're finding this presentation a little basic for your needs, you're hungry for something more, there's an advanced textbook out there, the Handbook of Milk Powder Manufacture. Again, please don't be put off by that it's milk powder. It has some great information. It's chock full of formulas and the rest of the physics, thermodynamics, and the rest of what goes on with a spray dryer. Also downloadable for free. So if you Google Handbook of Milk Powder Manufacture and Pisecki, you'll find yourself a PDF of this book. Print it out, keep it in your, keep it at work, use it for reference. I think these are great resources. Again, Missy said you'll get a link to the recording tomorrow. By me saying this, please feel free to use this for your own company training purposes if you find it useful. You have our permission, and the link's going to remain on the Caloris website. So feel free to look for it in the future that way, and our past and future webinars. I would like to take a minute for safety. We are talking about spray dryers. They carry with them the risk of dust explosion. We have the characteristics that we need. A dispersed cloud of dust, a confined space in the drying chamber or bag filter. Our product, that is the fuel, carried in air with oxygen. All they need is an ignition source. Diligence and vigilance are in this time. We are, a lot of us, out of the plants now every day. Working from home, we're not there with another set of eyes. The last couple of years, I've seen an uptick as we push our dryers for more capacity, more products to be run on them. I've seen an uptick in events, let's call them, explosions, fires, or near misses in spray dryers, particularly centered around what you might call holiday periods, Christmas holidays, summer shutdown. And if this time when we all are often out of the plants much more, it's the closest thing to a holiday we've got without it being a holiday. So this time we're in mirrors the type of situation during the holidays when these sort of events have been occurring more frequently. So be diligent, be vigilant, copy this minute of safety for your own meetings that you might be carrying out. I would say from a technical standpoint, spray nozzles in a dryer still remain about 90% of the source of fires and explosions. That's leaking nozzles, improperly assembled nozzles. Maybe you're not changing out the orifices as they wear so often. Make sure you have the spare parts on hand. Okay, orifices and spray nozzle parts aren't toilet paper. There's no run on them, but making sure you have those spare parts from your vendors are important. So Take this to heart. We'd love to see you all out there and your plants and your people, your coworkers being safe. So thanks for that minute. Diving into the presentation itself, we're going to look for some low-hanging fruit in your spray dryer, how it could be running better, how you could have tools to troubleshoot it better. So a basic spray dryer, I've chosen a basic model here. Your spray dryer may be different. There's lots of different flavors with internal fluid beds, different chamber styles, external fluid beds. Maybe you don't have a bag house, maybe you have a wet scrubber. But boy, when I get questions about spray dryers, when somebody calls me up and says, hey, I have a problem, it comes back generally to a basic heat and mass balance. My bag house is a problem, or my Cyclone is plugging up. I'd like more capacity out of my spray dryer, or a problem with the fluid bed. It comes back to needing some basic knowledge. And again, that comes back to spray dryer heat and mass balance. You might call it a thermodynamic balance. To be clear about things, mass balance, I mean, that's just the weight of things. That's the weight in pounds per hour or pounds per minute of all the stuff you've got going in and all the stuff you've got coming out. So that's stuff being air, water carried in the air, your product, water carried with the product, and the like. So we want to understand, to do this troubleshooting, we really want to understand the heat and mass balance. Whatever the problem is, it usually, unless it's a mechanical problem, it's usually contained, the solution is contained in understanding the flows of things, the mass of flow of things into and out of your spray dryer. So I have a little spray dryer model here. I've picked some product flow rate to come into it. That product is at an amount of solid, so I've picked 50%. So it's half product, half water, and it comes in at a temperature. For our little model of spray dryer here, we're going to get some product out based on the amount we've put in. In the perfect world that this spray dryer lives in, we're not losing product inside of the dryer. It's not hanging up, it's all coming out. But some of the water stays with it because you've got a moisture. In this case, I've said 5% moisture in the finished product. So we've got a little bit of water coming out with the product bound up in it, and it comes out at a temperature. We've got an airflow coming in. That air consists of the outside air, so the oxygen and the nitrogen and the argon and whatever else makes up air, plus some water vapor from humidity that comes in with it. Because we're trying to follow the water in this dryer, we need to follow the humidity, the vapor that's in our air portion. And finally, we're going to get the air out. Now my air out, balanced in this mass balance, comes out at a temperature. It consists of the air that went in, the vapor that went in with the air, the amount of water that got evaporated, all added up to be a new mass, a new weight of air leaving at a particular temperature. Now remember, we're talking about pounds. When we're talking about air, and that's sometimes strange to people, air is often talked about in CFM, cubic feet per minute. That is a volume flow. And although interesting and able to be converted to a mass flow using the density of the air at a temperature, at an altitude, we do want to evaporate a mass of water in the spray dryer, so we're definitely focused on a mass of air, a weight of air in pounds per hour to evaporate that weight of water in pounds per hour. So I do have a star up here on my diagram. There's one caveat, or one could find many caveats, especially if there's additional air streams from fluid beds and the rest. I do want to make note of one thing, and that is how you're heating your dryer, how you're heating this 400-degree air. A lot of cases around the world, and some in the US, where we're using indirect heat. So maybe it's steam through a steam coil, or an indirect natural gas heater that doesn't add in any water. But here in the US, we have a lot of direct fired natural gas heaters. So we might be heating the air up to 400 degrees using direct fired natural gas. And that adds water. Remembering natural gas is methane, so CH4, we're going to burn that in an excess of O2. And the other side of that equation is CO2 plus H2O. In our size here, in about 200,000 pounds of air, and we're going to heat that up to 400 degrees, you may be adding as much as 1,000 pounds per hour of water to your air by burning the natural gas. And that needs to be accounted for because we're trying to follow all the things that go through this dryer. So just a little note there. And we're going to assume that our dryer going forward is indirect heat. So we're going to forget that there's water being added through a direct fired gas heater. So there we are. But what we have defined in this heat and mass balance, or thermodynamic balance, is 16 things. We have 4 blocks, 2 things in each block, and 2 parameters in each of those 2 things, a weight and a temperature. So we know 4 things, what are coming in with the air. We're interested in 4 things about the product. So in each case, it's the air, it's the pounds per hour of the air in, the pounds per hour of the vapor in, the temperature of that air, and the temperature of that vapor. In the second group, it's the same thing with the products. And of course, it's the same things coming out. If you know those 16 things, you know your mass balance. If you're missing one, you can use formulas or a formula to calculate the others. But the more you're missing, the more numbers you don't know, or you don't know accurately, or you don't trust coming off your data system on your dryer, the more difficult it's going to be. The ones you don't know, you have to either find out through measurement, find out potentially through the laboratory, or calculate through a formula. So we need to know 16 things to understand this particular very simple dryer entirely. And if you're missing things, you need to calculate them through formula or get them through measurements. I hope that makes sense. It harks back to a little bit of equation solving through algebra. So if we want to draw a simpler diagram of this spray dryer, here's my simple spray drying chamber. I'm going to put some air into it. I'm going to put some product through it. So this is just a translation. I haven't changed the drawing from before. We're not changing the formulas. It's just saying the same thing in a different way. We're going to bring the mass in, so the weight in pounds per hour of the air and the vapor at a particular temperature. We're going to do the same with the product. So this is the spray nozzles now shown bringing product in with some water mixed in with it at a particular temperature. We're going to transfer some of that mass. Some of the water is going to evaporate out of the product and into the air. So we've got a bit of a mass transfer going on. That's what we need the formulas to help us figure out. We've got an energy transfer. That's a little harder. That's where the temperatures come in. We've got to figure out how much energy goes from the air to the product. And all of that gives us a mass of air out at a particular new temperature and a mass of the product out at a particular new temperature. So if you can grasp, again, these same 16 things, we showed 16 things in the last drawing, we get 16 things in this drawing. It's just a different way, a little more schematic way of saying the same thing. But 16 things, you're missing one, and we've either got to measure it or calculate it. So when you call me or someone like me out to your dryer, again, all that troubleshooting, my problem with the bag house, or I've got a problem with needing more capacity. We're not running as much capacity as we used to a few years ago. If we're trying to troubleshoot those sorts of problems, it comes back to the mass balance, and we've got to know these 16 things somehow. Or again, if you have a fluid bed, some additional things going on with your dryer, different air streams and the like, we need to know a few more things. But our simple model here, 16 things. So it's kind of concluding the theoretical side of this. We need 16 parameters, and the salient part is we need them accurately. If you want to know accurately how much more you can produce without clogging up your dryer and wetting down the walls, getting the most out of it and into a bag so you can sell it, we got to know these things accurately. So the 8 temperatures are fairly easy. RTDs, the temperature measurements, the probes on your dryer, if you've got them there, are fairly easy and they're accurate. So the first half is done. We've got a few simplifying formulas and we've already said them before. The amount of air you're going to put in, the amount of oxygen, nitrogen, argon, the air parts, whatever you put in, you're going to get out. We assume the dryer is leak-free, not losing a significant amount of air out a hole in it. What goes in comes out. And we're going to say the same about the solids. So if we're spraying in an amount of solids in your liquid feed mixed in with the water, we're going to presume it's all going to come out. If you want to sharpen up your model, you could say, well, I'm going to lose some to wall buildup. I'm going to lose some out of my bag house. But in our simple model here, we're going to say whatever we put in is going to come out again. But now we've got the harder ones left to figure out. And that's what we're going to spend the rest of the time discussing. We want to talk about the feed flow. So what you're spraying in as liquid and how to measure that and how to measure it accurately, and about the airflow and how to approximate that, how to measure it and measure it accurately. So that's going to be the second half of what we've got going on here today. So a little bit of the, how to apply this to troubleshooting, a little bit about improvements you can make, and a few simple tricks that people have taught me over the years that I want to pass on to you. So the first part, we're going to talk about feed solids going in. So that's our product going in. Are you running consistently? Are you feeding consistently? Are you making your feed consistently? And if you make it consistently, can you measure what you're making accurately? So that's the first part of the discussion. Now, I'll come into a plant sometimes and I'll ask the operators, so what do you think you're spray drying? What do we go into the control room. What are you drying today? And the operator will tell me about what they get from upstream in the plant. And they'll say something like, I usually get 26 to 28% total solids of my feed in the feed tank. So 26 to 28% of the massive things you're trying to capture, and the rest of it being the water or whatever you're trying to evaporate. Well, how often do you measure it? Well, we measure it once an hour. Record it, put it on our log sheet. Now, maybe you have a more modern HMI system and you have a data logging system and the rest, way better. But still often the operators know what's going on right now or what went on an hour ago. But how does this impact? How accurate is this? And how does it impact what's going on? To troubleshoot it, you got to know accurately what's going on. So I want to talk for a minute about what consistent feed solids really means. What would 1% higher actually mean? Not yet measuring more accurately. Let's say you're measuring accurately. Let's say your instruments are calibrated. You've got instruments with good resolution in them, but you actually want to get 1% more. Instead of them feeding you 27% from upstream, they're going to feed you 28% from upstream. What does that mean? So I'm following an example now of 5,000 pound per hour dryer. So 5,000 pounds per hour feed, liquid feed, coming to the dryer, 27% solids. That's going to give you 1,420 pounds per hour of powder coming out. It's still got 5% final moisture. So a little bit of that is water, what's coming out, bound up in the powder. And that gives you 3,580 pounds per hour of water evaporation. But now we want to get the guys upstream to feed us 1% higher solids. What does that mean? So I'm going to use the same amount of water evaporation. We're not changing temperatures. We're not changing airflows within the spray dryer. We're just going to thicken up the feed solids just a tiny little bit. And now we're going to feed in 5,080 pounds per hour of feed to the dryer, 28% solids, and we're going to get 1,495 pounds per hour of powder out. So, okay, 75 pounds per hour more out. But that's really a 5.2% increase in your production rate. So 1% more in the solids. This is what I'd like you to leave with, understanding this. 1% more in the solids is going to give you a 5% increase in your powder output. What would you do for that? What does that mean to your operation? Are you measuring accurately enough to do this? Are you operating consistently enough so that you could take advantage of this? And what would you do to get yourself consistent enough or measure it accurately enough? Well, that's 75 pounds an hour. I'm going to take a low number and say 5,000 hours a year. If you're running more than that, it would be natural for a plant, especially a dairy plant or commodities plant, to be running 7,000 hours a year, but I'm going to say 5. I think $1 a pound's a fair number. You know what your products are worth. I'm going to say you covered your overheads in your first 1,400 pounds of powder, and all of this is profit. You paid your salaries, you paid your energy costs, and you have a product that's worth $1 a pound, so your extra 75 pounds are worth all $1. Well, in a year, that's $375,000 potential on that 1% change in solids. Now, take this, do a screen capture here, take a picture with your camera phone of this slide and work these numbers for yourself. What are you getting? What are you getting consistently? And how accurately can you measure it day to day? And what does that mean to you financially? What would you, if you had that, if this works out for you in the same way, what would you spend on training to capture this? What would you spend on instruments to capture this? What other projects would you implement? Could you get even more? Could you get from 26 to 28? Could you take maybe your best of 28 and get 29% solids? There's economics behind this, and it's definitely worth making sure you understand, so you can have this dialogue about your plant, this understanding of your plant. So feed solids. We'll move on to feed rate. A couple of tricks here about feed rate, because we not only need to know what we're putting in, we need to know how we're putting it in, how fast we're putting it in, the pounds per hour that we're putting it in at. And if you have a feed flow meter, that's great. And if you keep it calibrated, that's fantastic. But calibration is a challenge. Keeping it calibrated is a challenge. And a micro motion type Coriolis meter is an expensive item, and not all plants have them. So what else could you do? Or if you need to make a comparative measurement, you, the engineer, need to go in and find another way to see, is the flow meter really accurate? Well, your nozzles, your spray nozzles are an orifice flow meter, and I want to show you how to use that. Your positive displacement pump. So if you're using a high pressure pump, that's a positive displacement pump. And so if you're using that, that's a flow meter as well. So let's take a look at those two. So high pressure pump is a flow meter. We know your high pressure pump will have a number of plungers in it. It might be 3 plungers, 5 plungers, whatever. That's a cylinder. And we can know its size. So it has a plunger diameter and a stroke length. So you can calculate each of the 5 piston sizes, the piston displacement. If you don't know it and you have your operation and maintenance manual, it can probably tell you there, or you can go back and call your manufacturer and find out what that piston displacement is. If you know the maximum speed, which will also be in your operation and maintenance manual, you'll know what your total maximum is. This particular example, 120 RPM maximum. So if we calculated out what this pump displaces and what it is as a flow meter, we would first recognize, okay, it's a liquid, so it's an incompressible fluid. We have a cylinder volume. In this case, that above calculates out to 497,000 cubic millimeters. So I'm going to say half a liter with every cylinder stroke. We've got 5 cylinders running at 120 RPMs. So that gives me 300 liters per minute. And the loose number that's in there, the approximation, because everything else is pretty tight so far, the approximation is the transmission efficiency. So I'm going to say this thing runs on a belt drive. The belts have a little bit of slippage. There might be a tiny little bit in the transmission itself. And I've found historically when I do this, 97% transmission efficiency is pretty good. So that's going to say that at maximum, it's going to be 291 liters a minute. Now, check that about your pump. Maybe your manufacturer's already taken this transmission efficiency in, and 300 liters per minute is already the reduced efficiency. And if it were slippage free, if it were 100% efficient, well, maybe you'd have 311 liters per minute. Do check that, because it does come into the accuracy. Now, we need to know how fast this pump's actually running. So we want to know, is it, you're not running it at 100% all the time. You're in control of it. It's on a speed drive. It's on a variable frequency drive. So you're going to go to the computer screen and you're going to say, how's my pump running? What's it running at? And somebody's going to tell you it's running at 50, right? Or it's running at 60 or 70, whatever. Make sure you know the difference of how it's running on the screen. Is it on a percent basis or is it on a hertz basis? What is the readout on the screen? If they're telling you 50%, well, then you've got to go 50%, 50 parts in 100, right, of the 291. If it's running on hertz, then it's 50 out of 60 hertz, and you're running a different number. My experience going into the control rooms, the folks there, they know their number, they know where it's running at, they know how it ran yesterday, but they may not know if it's speed or hertz. So do check that, or go to the speed drive itself up in the motor control center and check that. But that's an exercise you can use to verify what your flow rate is when you don't have a flow meter or you're unsure how your flow meter is operating. So your nozzles are also an orifice meter. There's lots of brands of nozzles out there. Delavan is very popular. Spraying Systems is very popular. They're both reputable manufacturers. No issue there. There are other manufacturers, Beat from Europe, Twist and Dry, Click and Dry, Twist and Dry, something like that. All very good manufacturers, no issues there. But each with their own catalog. and each with their own data about their nozzles. So do make sure as you follow this exercise, I challenge you to do it yourselves for your plant. Do download your data sheets from your manufacturer. I'm going to follow this exercise through as if it was Delavan nozzles. So Delavan has a PDF. You can download it. You'll need to know the type of nozzles. I followed this exercise through for their SDX nozzles. I'm going to say that this dryer we're talking about theoretically is using SDX5 nozzles. So I'm in the column for SDX5. You may have different ones. Nozzle consists of two parts, their swirl chamber and their orifice. So you've got to see what swirl chamber you have. I'm going to say I have SFV swirl chambers. And I'm going to say my dryer here, my theoretical dryer, has 109 orifices. So that's 0.109 inches in diameter. Every day your plant puts together their nozzles, presuming you have nozzles and not a rotary atomizer. Every day your team puts them together, and you're buying more replacement parts. You should really know what your nozzles are. It's probably hung up on a piece of paper or in a book in the control room, but to know what those are allows you to use the catalog from the manufacturer and find out the flow rates because they're all calibrated. So if I follow the 109 across the chart, I'm going to pass by the liters per hour, and I'm going to go to the gallons per hour size. And now we're going to want to know the pressure, and that's going to be on the high pressure pump or on a readout from the high pressure pump. I like to use the gauges for this that are on the high pressure pump itself to get the number. If the number is somewhere in between two values, you can of course ratio it linearly and get an average that way and find out where in between two values you should be lying. But here for this simplified example, I'm going to say we're running at 3,000 PSI, and that means that each nozzle would be 343 gallons per hour. Now, these are calibrated on water. It's slightly different for your product. The more viscous your product is, the further away from this number it's going to be. Dairy products at a 200 centipoise, 300 centipoise, I don't find to be too different. That's my experience. They're fairly close to this number, good enough to be a check on any flow meter that's in the plant, and certainly good enough when there's no flow meter. When you start getting into high centipoise, high viscosities, 1,000 centipoise, 2,000 centipoise, what might be high fat products, coffee creamers, things like that, then I might start trying to shift this number a little bit, or talk with the nozzle manufacturer about how they recommend shifting this number. So once again, you can use the chart from your manufacturer, find out what nozzles you have, the number of nozzles, the pressure, and get a flow rate in gallons per hour. You can know your density, your product density. Maybe you have to take a beaker of your product into the laboratory, get a volume, and weigh it to know what your density is. But you should know your density, and then you can calculate pounds per hour of feed. So using your nozzles as an orifice meter. So that takes us through the feed side, feed flow and feed solids. I want to go into the airflow side. We said we'd talk about airflow, needing to know airflow as part of your troubleshooting. So we're going to talk a little bit about pitot tubes, talk a little bit about fans, and a couple of other tricks to approximate, to get that wet finger feel for what your dryer is potentially doing. All right, air filters. This is an approximation. So this is a wet finger sort of, you walk into a plant, you're just trying to get a common sense approximation. You know, I calculated how much air was, or somebody told me how much the airflow was. Are they even close? Is this a right number? Well, one of the rules of thumb is for proper design of an air filtration system, each filter cell, and the filter cells are generally 24 inches by 24 inches, or in metric, 60 millimeters by 600 millimeters by 600 millimeters. Each air filter is generally designed for about 2,000 ACFM. So rule of thumb. So I've thrown a drawing of a filter box up here. And this filter box is 5 filters tall, 5 filter cells tall, by 10 filter cells wide. So when I look at this dryer, when you call me out to your spray dryer and say, Jim, help me with my dryer, I'm going to go look at the various filter boxes you have around there, and I'm going to say, all right, this is about a 100,000 CFM dryer. Now, again, we're in a volumetric flow, CFM. I need to find the altitude of your plant, the temperature of the air, and then I'm going to get a volume, a mass flow, and I'll convert that into pounds per minute and pounds per hour. But it gives me a very wet finger approximation. Now, that's if the dryer designer designed this well, if it's still running the way it was designed, and there's always a little bit extra. They probably didn't need 50 filters. They might have only needed 47. But 50 makes a nice square, 5 by 10, so it probably has a little bit more in it. But still, it gives you that basic fundamental approximation to know how much air is moving through this system. So airflow approximation, step one. We want to get a little closer. We want to measure it more accurately. We're going to do it by pitot tube. So just because we're maybe a little bit more used to seeing pitot tubes in our life than we realize, pitot tubes are a device used to measure airflow. For your next pub quiz that you go to, you can have this fact. Henry Pitot invented this in 1732, and he was using it to measure water flows on the Seine River. It's subsequently been realized it can be used to measure airflows, and it's on the outside, multiple on the outside of every airplane, measuring external flow. We can use a device like is shown here on the left to measure internal flow inside of a duct. We're going to measure the total pressure on one leg of this, the static pressure on the other leg of it, and we're going to use those two to get a dynamic pressure differential, or commonly the pitot pressure. So we go into a plant and we want to measure it, and nothing is ever ideal. You might have a digital manometer. Here you can see it hooked up on one leg and the other to two inputs on the digital manometer. You could have a handheld pressure gauge, like a Dwyer MagnaHelic or something like that. You want to go into the duct and measure it. You're only going to get a highly accurate measurement if you have fully developed airflow. So it's not faster on one side and slower on the other. Well, we never live in a perfect world. Our dryer ducts are never as long as we'd like them to be. So we've got to do some work. We've got to do pitot traverses. If you have a round duct, you want to go across the duct, up and down the duct, get some averages across these, do concentric areas, again, equal concentric areas. The inner area is the same as the area of the outer annulus, and you've got to plan these measurements. So you can get an average, an accurate average. If you have a square duct, you can do the same thing. You want to set up an array and measure it this way. But once you have that, and once you have an average, you can get use the formula, and it's available from the manometer manufacturers and in textbooks and the rest. But you're going to measure a differential pressure. You're going to know your air density for your altitude and the temperature. You're going to divide that, or you're going to use the gravity constant, and you're going to get a velocity through a squared factor, so that you can actually get the velocity in the duct. From that, you're going to know the cross-sectional area of the duct, and therefore you're going to get a flow through that duct. So a bit of a complicated procedure, but still the best way to try to get an accurate airflow measurement through the duct. A small amount of equipment, a little bit of work and knowledge, and you're going to get a good reading. So a couple of caveats about pitot tube measurements. If you have too low a velocity in the duct, and I'm going to say that's 20, 30 feet per minute, something like that, you're not going to get enough of a differential pressure. You're going to get too low of a differential pressure, and it's going to be imprecise. Spray dryers are usually above that, so that's not terribly much of a worry, but do be aware. If you have too high a velocity, now it might not quite be turbulent. It might be starting to enter a turbulent regime. It might start shedding some vortices, so you get high or turbulence in one part of a duct or another. But high velocities are not going to be really that valid either. So do be aware of that. Again, spray dryers don't really come up with that, but I feel it's worth saying. Third caveat for perfect measurements. Now, perfect measurements, you want to get about 8 straight duct lengths upstream of your measurement point, about 2 straight duct lengths downstream of your measurement point, That's why we're saying in a spray dryer, it's going to be an approximation. You want to go use that ratio, 8:2. Or if wherever you're going to take the measurement, go as far downstream as possible and get the measurement there before you enter an elbow or an expansion in the duct or something like that. So some limitations around using pitot tubes. Your Cyclone, if you have a Cyclone on your spray dryer, it's also a Flowmeter. This is the formula by which you can calculate the airflow through your Cyclone. I've used metric in this calculation, so the airflow in kilos an hour. There is a constant in it that makes it a little bit hard. The constant, it has to do with the exact geometry, and that could come from your manufacturer. Or if you're trying to compare the same Cyclone, the way it runs today, to the way it runs ran a year ago or 10 years ago, if you have data, you can equate both sides of the equation and cancel out the K factor. The diameter, in this case in meters, the air density, and your pressure drop on the Cyclone. Pressure drop in this case is millimeters of water gauge when you're using all of these other factors in this formula. If you're going to do it in imperial units, just check a textbook and make sure you're using the right units to get the right outcome. Again, by the formula, if you know the original design of the airflow, so you have a new dryer, you're still in contact with the manufacturer, you can find out your K value for that Cyclone, or you know your dryer is running at design. You have a dryer designed for 40,000 pounds per hour, 20,000 kilos per hour, whatever your number is. You can calculate your K and keep that up your sleeve for future measurements. A bit of a trick from experience is that most high efficiency dryer Cyclones are designed for about 150 millimeters of water gauge, 6 inches of water gauge. Higher than that, you're kind of not, you're getting too much separation efficiency, meaning too much smearing of products, or you're not gaining anything for the extra energy you're putting in. So a lot of dryer Cyclones, I would say the predominance of them out there are going to be in that 150 millimeter range for their design. So you could use that to calculate a K factor. You're trying to calculate to that against how your Cyclone is running currently. Now we're into that troubleshooting situation. How much airflow do I have? Why is my dryer running the way it is? Well, today, for example, you're only getting 3.5 inches of water gauge pressure drop when you measure between the inlet and outlet of the Cyclone. Well, 6 inches to 3.5 inches, that's about 41% lower on the differential pressure, and that gives you about 23% lower on the airflow when you equate that through the formula. So again, a handy tool, the more precise your K value is, the more precise this is going to be, the more precise you make your measurements, the more precise it's going to be, but it does give you a handy tool for making an approximation. So moving on to fans. Fans they really define your airflow. They get made, they get built, originally delivered from a manufacturer who designs them to move a certain amount of air at a certain static pressure. And they can provide you with design information. If you have that initially, hold on to it. It's like gold. If you don't have it, they should be able to reproduce it for you, and you should be able to get it. We're talking about a document that looks like this, a fan curve that shows a ratio of a static pressure and an air flow. And also will be on there the brake horsepower that gets used. In the top of the document, it's going to show you the air flow. Again, you can change that over to pounds by using the air density, but it is only valid at a certain static pressure. So you have to check, are you still running this dryer at the same static pressure that the supply fan was designed for? Is there as much resistance as was originally designed? Did I add something in to my airflow stream that adds resistance? And maybe that's choking the airflow? Did I remove something that's lowering the static pressure and allowing more airflow? So as we move into the last couple of slides talking about that differential pressure, you can do the same exercise with your exhaust fan. I've chosen to show an exercise with the supply fan. In the front of your supply fan, you've got some filters, but you're taking air from outside, most likely. Maybe you're taking it from in the building, but most likely you're taking it from outside. And generally your air pressure there is 0 inches of water gauge as an absolute measurement at the air intake. The other thing we know as we move from fan to heater, up the hot air duct, air disperser, and drying chamber, is that in the drying chamber, you're going to have some value. You're going to know what that is. And in my example here, I'm using minus ½ an inch of water gauge as my chamber pressure. So what's going on in between the two, and what work is the fan doing? So after the filters, so right before the fan, right after my filters, I'm going to measure a new pressure, an absolute pressure. So one leg of my gauge is connected and the other one is reading the room pressure to get an absolute pressure. And I'm reading minus 2 inches. So that's telling me there's about a 2-inch pressure drop across the filters. Cool. It's just information to know as you do this buildup and this troubleshooting. I'll give you this is where your variability comes in. If you have clean filters, I've chosen 2 inches for this example. If you have clean filters in there, you might be at 0.1 inches. You might be at 0.5 inches if you have HEPA filters in there. You could have very dirty filters. When was the last time they were changed? That might lead you to 5 inches of pressure drop across the filters. And all of that is variable. That's why we want to measure it, because we want to know how we're running at the time we're making the troubleshooting analysis. But my example, we've used 2. So now I'm going to work backwards from the other end. I'm going to measure up here at the inlet to the air disperser. I'm going to take a pressure measurement there, again, an absolute pressure measurement at that point. And that tells me that I've got 6 inches of differential pressure across the air disperser. I work backwards from there. I'm going to take a temperature measurement after the heater, after the burner, and I might have 8 inches of pressure there in my example, absolute pressure. And that tells me I have 2 inches of pressure drop down the duct, around the elbow, and to my next measurement point. So 2 inches of pressure drop. I come backwards and I measure before my heater, and I now have plus 12 inches of pressure drop, which means a 4-inch differential. 12 minus 8 is 4, a 4-inch differential across my heater, burner, or coil. And that tells me something about the fan. That tells me that in this measured example, I just went out to the field and measured this. This measured example, this fan is running at 12 inches of static pressure. And now you can go compare that to your fan curve and say, oh, this fan was designed for 18, but it's only running at 14. That means the curve isn't really quite valid. You don't go to a different place on the curve. That curve is valid for that airflow and that static pressure. If you have a different running condition, you need a different curve. And your manufacturer, your fan manufacturer, can produce that for you, or you can use their online tools. So I chose to look at New York Blower. I have no preference for New York Blower. They're a good company making a good product, but the other fan manufacturers have the same types of tools where you can go to their online tools. New York Blower calls it fan to size. You can put in some data. You can put in your model number if you have it, or your wheel type, or you can use your serial number. You can call them up and talk to them and find out what's going on and get that data. If you have it, you can use their online tools. This is even the New York Blower iPhone app that does the same thing. So really want to challenge you. If you have the time, if you have the inclination to go out and know this with a little bit of work, you can know your dryer really well, so you can know those 16 things that we talked about at the beginning to troubleshoot your dryer. So with that, I'm going to wrap up, put the challenge out there for you, give you a little homework. You know, we showed the 2 books at the beginning. Go out and download those copies, get those PDFs. I'm not saying read them cover to cover, but become familiar with the content. So when you need some help with troubleshooting, you know where to look in these books and how they can help you. I challenge you to know your dryer feed solids, how you can measure those solids, confirm the density of your product with the lab, estimate the accuracy of your instruments. Know your dryer feed rate, do the 2 exercises. Get the data on your high pressure pump and its piston displacement and calculate the feed rate that way. See how it compares to the nozzle chart and your estimate of your feed rate from that and how it compares to your Flowmeter. Use one or more of the methods to estimate your airflow. Get the manufacturer's fan data. Keep it. I mean, if you're inviting someone like me or someone like me out to your plant, we're going to need this data anyway. And we're going to get to the bottom of your difficulties sooner if we have it at hand. So go out there, work with the manufacturers, collect the data, keep it in a place in your plant. And if you'd like a little extra credit, you're that person that finds this easy and wants to do something more, recognize that especially on your supply fans, you're going to have differing conditions between summer and winter air conditions. Go out and ask for your fan curves under both sets of conditions, and take a look at how that affects the amount of air you're moving through your plant and what that might do for you. So with that, I'm going to say thank you very much. Once again, thanks for investing your time in our webinar. I hope you found it helpful. Missy's going to take some questions now. I'm going to stay on the line. You can reach out to me. You can reach out to Caloris, and you can look for any of us. You can look for the Caloris page on LinkedIn. You can look for my page on LinkedIn. Go ahead and link to me. I invite you all to. And I really look forward to your questions. So thank you very much.
All right.
There you go, Missy.
Yeah, we do have a couple of questions that came in. The first one was, could you touch on instrumentation that can quickly ID percent solids?
Oh, not my forte. So I'll say that at the outset, that it is not my forte to do that. But instruments that measure percent solids, I think that the Coriolis type flow meters have a function in there where you've got to calibrate it in a laboratory to get that. So you take some samples to the laboratory, you create a data table, you get that data table and you put it in the Coriolis flow meter when you program it, and then you can be getting solids out. It's really a density that it's looking for. It's an expensive device, so it's a $10,000 instrument, and then you've got to install it, wire it, and the like. But it does give you that data. So
Okay.
I think that's what I would recommend.
The other question I have is, when you say flow meter, are you referring to the flow meter coming off the evaporator, let's say in a condensed skim application, assuming your dryer balance tank is keeping a steady level, product in the tank would equal product out?
That's correct. I mean, so thank you. Whoever's asked these questions, thank you. And again, we'll stay on the line until they're done. But yes, in the conditions you just described, if it's the evaporator flow meter and you're keeping a constant level in the dryer feed tank and you're not adding water anywhere through a direct steam injection heater or anything like that, then yeah, then that evaporator flow meter is going to be the same. What I've presented today is a bit theoretical, and we would want to know the theoretical feed into the dryer. But practically, you've described a situation that if you're holding the same level, you're not emptying or filling the feed tank, you're going to get a good reading off the evaporator outlet meter.
Okay, and if you could stop your screen share there, Jim. I do have one other question that's come in. Why are there 2 air removal ducts in your fluid bed design?
Why are there 2 air removal ducts in my fluid bed design? I'm not sure where they're referring to that, but only from circumstance. A small fluid bed will work adequately well with 1 air outlet from the fluid bed. Large fluid beds might have 2 or 3 air outlets taking the air away. So it really comes down to the size of the fluid bed, whether you have 1 or 2 or more. And I hope that answers that question.
Okay. If anybody has any additional questions, we do have a couple minutes and you can use that Q&A feature to ask. But in the meantime, I've brought up a slide that is an advertisement for our upcoming webinar next week on MVR evaporator upgrades. This will touch on equipment that may be existing in plants that have been around for 3 or 4 decades. These evaporators often incorporate antiquated parts that there's better solutions out there for them now, and we'll go over some solutions that will provide some peace of mind for operators in terms of safety and capacity. And so if that is of interest to you, you can follow the link you see there, caloris.com/caloris-webinars. That's where you can also find the recording for this and our past webinars and registration links for other upcoming webinars. If you would like to stay in regular touch with us, we are offering a weekly e-newsletter now, and you can sign up for that by scrolling down to the bottom of any page on our website and entering our email address to be added to our e-newsletter list. If you have any questions you didn't want to ask in the webinar setting, you can feel free to send email to info@caloris.com. That goes directly to me, and I will do my best to answer your question or forward your question to the appropriate person. I do have one additional question that's come in. What would you recommend if your evaporation rate on your dryer has changed?
Okay, I saw that one come up. I'm learning to use these tools. So if your evaporation rate on your dryer has changed, so that question could be taken two ways, and I'll try to look at it quickly from both sides. Did you change it on purpose? That may have implications. If you've changed your evaporation rate through more airflow, maybe your air disperser isn't designed for that. And you have too strong a jet of air going to the bottom of the dryer, and you're having buildup problems because of it. There are various implications about things in your dryer that are designed for a certain set of conditions: airflow, temperature, evaporation rate. If it goes the other way, just through circumstance, we have a diminished evaporation rate. It used to run more, and we can't get it to do it anymore. Now it runs much less. Well, that's the troubleshooting we've sort of gone through today. We need to know why. So we need to know airflow, we need to know product, we need to measure it out precisely. So I would say if it's that diminished evaporation rate situation you have, let's apply a little science to it, a little rigor, and make the measurements, and then we can actually answer that question of why. So I hope that helps.
All right, with that, I just want to solicit any suggestions for future webinar topics you would like us to cover. We have webinars scheduled weekly right now through March 21st, and we're continuing to look at topics that would be of interest to everybody. So please feel free to shoot some ideas to us either in the chat here or by sending email to myself or Jim. And with that, I want to thank you, everybody, for joining us. I hope everybody has a great rest of your week and stays healthy and safe.